Hello and welcome back to another VMK in the game development series. In this VMK we're going to start working with the parser. Now in the past what we've done is anytime we started working with a new component of the game engine, we jumped right into Visual Studio and started adding the classes and writing the code. Well, with this video we're going to do things slightly differently. Because the parser itself is almost a separate module, what we can do is create a new project in Visual Studio, program the general functionality of the parser, and then once we're certain that it's working correctly, we can then take that code and port it into our game engine. Now we want to do it this way rather than going in and trying to program the parser directly into our game engine, because it'll be a lot easier to debug. You'll notice that there's going to be a lot of minute details inside the parser that we need to take care of. And it's best that we isolate the parser code as much as we can so that we can debug it systematically. Once we know that it's sort of working, then let's go and put it into our game engine and tweak it some more to get it working with our game engine. So that's the approach we're going to take. So let's get started by going into Visual Studio here, and I've just opened it up with no project loaded just yet. What we're going to do is go under File, New Project, and we want to create a new Win32 project, and it's going to be a console project rather than a Win32 project. This one was one that we use Windows. This is just a purely console-based, like a DOS program. And you can name this anything you want. It doesn't matter, so we'll just call it parser for now. We're going to rename this later on once we import it into our existing game engine. And click, let's see, what do we have under here? This is fine. Click OK. And under Application Settings here, we want to create a console application in an empty project. So click Finish. And this creates our Visual Studio files so that we have our project. Now you'll notice inside of our project we don't have any source files or header files. It's completely blank right now. And inside our class view you'll notice we don't have anything here. This is exactly what we want. To start off, we're going to create a source file. So click up here and we want to add a new item. We want to add a CPP file. And let's call this parser also. So here's our blank file that we're going to start writing our parser code in. At the top, we're going to go and include windows.h. We're going to include iostream.h, or don't add the .h, it's just iostream. And we're also going to include string with no .h at the end. These three include files will be the general things we're going to be using to implement the parser. Now, as described inside of the PDF file, remember in the previous video I created this PDF that sort of outlined how the parser is going to work. And down here we said each line of text should not exceed line max length. So this here is a variable. It's actually a defined variable, which we're going to be creating, and it's going to be set to 300. So let's go and implement this here as a define line max length, and we're going to set it to 300. Notice that there's no terminator at the end of a define. We might as well start off with the main function, so we type in int main, open the brace, and we should return 0 if everything is okay. Let's just save this, compile it, make sure that everything so far is okay. And it is. Okay, so this is our general structure. Now, what is it our parser is going to be doing? Well, we need to open up a file, and when we open up the file, we want to open it as a text file, not a binary file. So to do that, we need to create a file pointer. So I'm just going to call it FP for pointer to a file. And we're going to set this file pointer equal to, we call a function called fopen, which opens any file on a computer. And the file we're going to be using You can name it whatever you want, but as I said before, inside of the PDF here, we're going to be calling a function, I guess I didn't mention it here, but the file that we're going to be opening is going to end with .lvl. So in here, I'm just going to call it, I don't know, testing maybe, .lvl. And how do we want to open this file? Let me just go back here. So the first parameter is the file name that we're going to be opening, and the second parameter is how we want to open the file. So we want to open it for reading and to be a text file. So that's what the R and the T stand for here. Now we have to check to make sure that this FP parameter is not null. If it is, then that means this file doesn't exist, so we should just return -1 and quit the program. If the file does exist, then we'll go down here, and just as a little test here, we can go printf opened file. This will let us know that our file has been opened. And again, let's compile. Actually, this time we should build. Now we want to run the program to see if this actually does something. And actually, let's do this. Printf file doesn't exist. All right. Now, if we press this button here to start running the program, you'll notice that it ran and the window that it created disappeared immediately. What that's doing is it's running through the program, but then automatically Visual Studio is set up to close the window after it runs. So you can't really see what happened in the program. You're not quite sure whether it went into here or went into here. Now there's a couple ways to get around this. What we can do is go inside of our folder here where we have our Parser project, and under debug you'll notice we've compiled that parser.exe file. If we double click on this, we get the same problem. You'll notice, I don't know if you'll actually see this in the video, but if you just double click on it, it runs really quickly and then closes the window. So that doesn't help either. So let's try something else. Let's go under the command prompt inside Windows here, and you'll notice I'm in the same directory as the parser. So let's go into the debug folder, and in here you'll find a parser.exe. If we run parser here, you'll notice file doesn't exist. Now we can actually see the output of the program, and this window stays open because we opened up the window manually. Now you don't want to really go into DOS and have to run your program this way to see the output. It would be nice to run it directly through here and actually keep that window open. What you can do is underneath the debug tools, you'll notice there's Start, which is the one we're currently using, but then there's also Start without debugging. So the hotkey for that is Control F5. If we press Control F5, you'll notice now the window appears, but it doesn't close automatically. It stays open for us until we press any key to continue. So there's a message here saying to do that. As soon as we press any key to continue, then the window will close. So this is the way we're going to be using Visual Studio to debug our program. Instead of using this button up here, we're going to be starting the program without debugging by pressing Control F5. Now, to fix that little error there that we saw with the string itself was sort of concatenated all on one line, we can get around that just by putting a new line character at the end of our error messages here. So if we do this and then compile, build, and run our program, you'll notice now file doesn't exist, carriage return, press any key to continue is shown on the screen. Alright, so we got that. Now, it's giving us the file doesn't exist error message because testing.lvl doesn't exist, so we haven't created it yet. So let's go ahead inside here and create that file. The easiest way to do this would be just to go and create a new text file. Let's see here, text file. And we called it testing.lvl. So as soon as you rename the file to be testing.lvl, it'll ask you, do you want to change the file extension? Hit yes, and now we've created this file. Now notice where I've placed this file. It's underneath the same folder as parser. It's not inside the debug, it's directly in the same root where our parser.cpp file is located. This is important because when we run the program, it's actually running from this location. So now if we go and press Control F5, it says open file. Alright, so we can open the file, that's great. However, anytime we open a file, we have to close the file or else there's going to be a memory leak. So because I didn't program a single line of code right now, I just leaked a little bit of memory in my operating system. Not that big of a deal, but if you continually do this, it's going to make your operating system unstable. So make sure you don't have memory leaks in your program. Alright, we know that the file is not open when it goes into here and it quits, so we don't have to do anything additional. If the file does get opened here, before we exit our program, we should close it. And the way we do that is we call fclose and we pass in our file pointer, like so. So now we can be safe that anytime we open the file, our program will close it so that we won't have a memory leak. And I pressed the button up at the top so our window disappeared. But if we press Control F5 again, now you'll see open file, press any key to continue, everything's fine now. Now there's one other thing I'd like to do before we move on, and that's add our testing.lvl file into this project. And we can do this by clicking Resource Files here, right click, click Add Existing Item, and under here just specify All Files and select that testing.lvl. Now you'll notice that inside of the project we have our testing file, which we can just double click on and it will open up inside Visual Studio. So in here we can go and type text to make modifications to that file. And from in here we're going to be loading in this file and then parsing it to see whether that data inside of that file is valid. Okay. One other thing we could add in here is just a printf function that says we're going to be closing the file. So let's just go and run this, make sure it's all okay. So we open the file, we close the file, and then asking us to close the window. Now, let's begin by writing the following code, which will start parsing our project. Okay, what we have here is I created a variable called SZData, and it's an array of characters which contains up to a maximum of 300 characters long. We also create an integer which is initially set to 0, and this is going to contain our current line number that we're parsing. What we do is we call while, and the parameter inside of the while statement, fgetS, SZData, line max length, fp, and then we check to see if this is not equal to null. What this is doing is it calls this function fgetS, which basically says take a line of text from this file here and store it inside SZData, but only store up to a maximum of line max length characters. So in other words, only store up to a maximum of 300 characters. And it knows which file to look through because we're using the file pointer as the third parameter inside of this function. So that's what this function does. It returns null if fgetS cannot find this file or cannot read anything else from this file. So we check to see if this is not equal to null. So if it's not, then that means we have read something and it's now stored inside SZData. So what we can do is we can increment iLine by 1 so that we know that we're now looking at line number 1 from this testing.lvl file. And we do a couple checks. We check to see if this line of text, SZData, is valid, first of all, by checking to see if the length of that line is less than 3. If it is less than 3, then we just call continue, which means go to the beginning of the code here to while, and then call this fgetS again a second time. So in other words, if we have a blank line of text here somewhere, like something like this, the program is going to go in here and load this in. It's going to go here and it's going to find how long is the line of text that is stored inside SZData. If it's less than 3, it's just going to skip it and then continue on. If the length of the line of text is 3 or more, then we check to see if the beginning of SZ data begins with 2 slashes. And you remember that inside of our document here, we've outlined that 2 forward slashes represents a comment right here. So we check to see if it's a comment. If it is, we again skip the line of text. We don't need to parse whatever else is inside this variable. So we'll continue on to the beginning of while and get the next line of text from testing.lvl. We also check to see if we found the word END, because this is the trigger that says, okay, we don't want to parse beyond this point. If we do get to this point, instead of continuing, we actually break. And break will actually exit the while loop and then continue on down here, rather than continue on and go to the next while statement. So that's how we handle the end. Oh, and there's one other check we do. We check to see if the length of the string that we've saved here is less than 9. We know for sure that all the keyword structures that we've created here, we have box, cylinder, and so on, all of these have certain requirement fields, and because of this, I calculated what is the minimum size of text that is required per line, and it happened to work out to be 9. So if it's less than 9, we know we have an error because it's not possible to have a keyword plus some parameters and on a single line of text to be less than 9. So if this does occur, we say line number whatever has an error, the line is too short. And then we continue on to the next line of text to parse. Alright, if we've gotten down to here and we haven't broken out or continued through, then we're going to call this function called parseLine, and we pass in SZ data as a parameter. ParseLine is going to return a true or false value, which is going to determine whether the line was parsed successfully or not. If it's false, then this negated operator will set the parameter true, which will mean this if statement will execute, and we're going to say line whatever has an error. Otherwise, we're going to continue on through to the next line of code here to get parsed. Now, because we haven't implemented parseLine just yet, we can't run this program, but what we can do is at the top here, we'll create a function called parseLine. It's going to take in a char star, and we're just going to return true always, just so that we can test this program as it is right now. Okay. So when we run it, we see we have an error on line 1, 2, 6, and 8. All of these are too short. Okay, let's take a look at our file. Why are we getting this error messages? Well, 1, 2, 6, and 8, 1, 2, 3, 4, 5, 6, 7, and 8. All of these happen to be less than 9 characters long. So we're getting all these error messages. Alright, well, let's make them more than 9 characters long. Just putting in garbage text here just to do some testing. Actually, let's make this one 4 and this one like so. Now, if we run the program, you notice we only get one error message. Line 4 has an error. Line is too short. So these ones here actually went through our code all the way down to here to get parsed, and it went into the parser, which returned true, so it didn't generate any error messages. The one long line of text generated an error because, or the short line of text generated an error because it went into here in terms of the execution because the line was too short. Now, we can test this other thing here. We can test comments. So let's see here. Let's make some short lines of text. And if we run this, you'll see we have line 1, 2, and 4 bringing up error messages. But if we put a comment in front of each of these and rerun the program, you notice now we don't have any error messages because the commenting of the line took care of the code so that we don't actually go into here to say that we have an error. Another thing we can test is this end here. We know that if we take these comments out, we're going to have 3 error messages. Well, if we put in the keyword end after the first one, we should only see error on line 1, and that's it. These two will not generate an error message because they don't actually get executed. So, press the wrong button, Control F5, and there we go. We see we have line 1 has an error, line is too short, and then we close the file and that's it. So, up till now everything seems to be working fine. What we need to do now is go inside of parse line and actually program the code to start parsing it the way we want to parse it. Okay, so what do we have here? Inside parse line, we have an if statement structure that we've used to find either box, cylinder, grid, material, texture, transform, shape, light, or the plus. If we don't find one of these keywords inside setData at the very beginning, then we go inside of this else statement here, printf unrecognized keyword, and we return false. Otherwise, we return true because we know that one of these is successful. So now, you're probably wondering, what is it that we do inside each of these if statements? Let's start off with an easy one like the box. You'll notice that there's a lot of code in here, but it's actually very modular. What we do is we printf box and a bunch of dashes just so we can show visually on the screen that we're working with a box now. And first thing we do is we look for the required key field. And inside here you'll remember that for the box keyword we have GOID as the required field. It has a little heart beside it. Cylinder also has GOID, grid has GOID, light has a type that's required, and so on. So the first thing we do is we look for the required field. And we do that by using this function called findKeyword. We pass in under the first parameter what it is we're looking for. So we're looking for GOID. The second parameter is this value that's calculated here, and I'll talk about this in a minute. And the third parameter is what is it that we expect to find associated with this option. And for GOID, we know it's going to be returning an integer, so we need to have an integer returned to us. And this function, findKeyword, will also have a return value, and if it's not equal to return OK, then we set this return to be false because we know that there's something wrong with this box structure. Same thing for the width, the depth, and the height. We just change the parameter that we're looking for, as well as what is it here that this parameter is associated with. All width, depth, and height are going to be floating point numbers, so here we have return float. Now notice that we're not looking for return OK because these ones are optional, so they may not be found. If that's the case, then this function may return to us return error no value, and if it does return something greater than or equal to return error no value, then we're just going to return false. So what is all these return int and return OK things? Those are actual enumeration structures that I created. So we first have to go up here and define them before we can use them. So at the very top, we have an enumeration return type, and these are all the different kinds of values we expect to find inside of our parsing file. So we're going to be looking for characters, so these are strings. We're going to be looking for integers, floating point numbers, an array of 2 floating point numbers, an array of 3 floating point numbers, and an array of 4 floating point numbers. The return types that we're going to be allowing are return OK, return not found, return error no value, and return error duplicate. And I'll talk about these in more detail once we actually see where we need to use these. Our function here, findKeyword, is structured like so. It returns an error type, so it's going to be returning one of these, and it takes in 3 parameters. It takes in a pointer to our keyword, so that's the first parameter. It takes this value here as an std string, and I'm just storing it in the variable sData. And the third parameter, the return int here, happens to be a type of return type. So we pass in a return type into this variable here. So at the very end here, I can just add this, And for now, I'm just going to return OK for all of them, just so we can do a quick test. Okay. We should be able to compile this now. And let me just do a quick search here. Okay. So let's go and run our program as it is. You notice we get an error on line 1. Line is too short, and it closes the file. Well, let's go inside here. We have an error now because this is too short. So let's go and change this to box. We know that box is a valid keyword. Let's go run this. We notice we still have an error on line 1. Line is too short. We cannot have box without having the required key field. Required ones here are GeoID. So let's go into here and type GeoID underscore, and let's just give a number here, just 1. Now let's run the program, see what it gives us. Unrecognized keyword, line 1 has an error. Why is it giving us this? Well, if you look closely, you'll notice that inside of our parser, we're looking for box with a capital B. But inside of our file, we have box with a lowercase b. So the parser itself is not case insensitive for the keywords. We need to specify the cases correctly. So now if we change box to a capital B and rerun the program, there we go. We notice that it found the word box, so we typed in that box with the dashes all the way across, and then it closes the file. It didn't display anything else because all this other stuff here, it doesn't do anything yet. We don't actually extract any numbers from the file. All we've done is we've identified that this line of text that we're parsing starts with the word box. So we print box out, and then we went through all of these. These didn't do anything yet. And then we printed 2 new line characters so that we can sort of have a nice structure. You'll notice this if we go into here, create a bunch of other boxes, rerun this, we now have 1, 2, 3, 4 boxes because we have 4 boxes inside of our testing.level file. Okay, so now what we need to do is go implement this find keyword function. And the find keyword function is basically the heart of the parser. It's going to go through each line of text in here and break it apart and try to extract all the data that's inside all the parameters that are in here. And this is a little bit complicated, but if you go through the help file inside MSDN for any specific function that I use, you should be able to step through and figure out exactly how everything's working. Oh, one thing I just noticed here, I didn't explain this str LWR function. What this does is we're taking SZ data, which is our array of string for 1 line of text, and we're taking all of the values starting from here. We're starting from the 5th character inside of the string, and we're changing it all to lowercase. The function itself returns a character pointer, so then we take that character pointer and we pass it into find keyword. We take the string of text, which we know is going to contain something like this, box space GeoID underscore 1, and we say, okay, we're going to be looking for this parameter here, GeoID underscore, and we want to start looking for this thing at the location of the string starting from index number 4. Now the reason why I use index number 4 here is because we don't need to do a search for GeoID from index number 0, because index number 0 is going to be pointing to the B inside box. So we know that box is going to be BOX, so this is going to be 0, 1, 2. The space is going to be 3 after box, and number 4 is the next character in the string. So in other words, here we go. We have index 0, index 1, index 2, index 3, and then index 4 is going to be the start of whatever is located right here. It doesn't necessarily have to be GeoID. It could be actually anything. It could be the width parameter. We could do something like this, in which case this is still fine because this string here, str lower, takes whatever's here, so starting at index number 4, and converts everything from there onward to be lowercase. Then that parameter is what gets passed into find keyword. Let's go into PaintShop Pro to see if I can make this a little bit more clear. Okay, let's say we had the following scenario. Someone passes in this string into our SZData parameter. So we have box space GeoID underscore 1, then there's a space width underscore 20, and then we also specify a height underscore 15 here. The way that our C++ code is going to interpret this is it's going to save this SZData inside of an array. And the array will look something like this. So starting from here, this is going to be index 0. And each character to the right is going to increase the index number. So this is going to be index 1, index 2, index 3, index 4, and so on. Now, as I said before, inside of our parser here, we're taking the 4th indexed value of SZData, and from there onward, we're going to convert everything to lowercase. Well, we can see this here now more clearly. The 4th parameter is going to start here at GeoID. So basically from here onward, all the way down to the very end of the string, all of the characters here are going to be converted to lowercase. So that's all that code does. Whenever I describe how find keyword works in detail, we'll go back into PaintShop Pro. But for now, let's just continue on with parse line to see what else we do here. So we've got the GeoID, which is the required field. And then we also look for the width, the depth, and the height, because those are the other parameters that box is allowed to have. And then after that, we're basically done with the box, so we don't look for anything else. The other parameters, which we do parse, is the cylinder, the grid, and so on. So let's take a look at what we have here. You'll notice that it's basically the same thing that we did here with the box, but for a different number of parameters. So for cylinder, we have the GeoID again, and then we have the number of sides, we have the radius, smooth. Now notice smooth here is an integer, as well as the number of sides is an integer. So this is a little bit different than what we had in box, because box we only had floats. GeoID was an integer. So keep an eye on what we have here as the type, as well as what the parameters are that we're looking for. And height here is a floating point number that we look for. For grid, we have the following. We have GeoID, an integer. We have the width, the depth. Both of these are floats. And then we have the number of divisions in the X and the number of divisions in the Z. And both of these are integers. Now notice here, the grid keyword is 4 characters long. So to include the space and the character after that, we now index number 5. This index number will always be the length of the keyword plus 1. So here you saw cylinder was 3, so 3 plus 1 is 4. Here we have grid, which is 4, so 4 plus 1 is 5. Here we have material, which is 8, so that means that we're going to be indexing for number 9, just as shown here. And the parameters that we look for are material ID, which is the required field, and then the optional fields are the ambient color, the diffuse color, the specular color. All of these are floating point numbers, but it's going to be 4 floating point numbers stored in an array. So we have float array 4 here. And let's see, diffuse, specular color, emissive color, and shine. Shine is just a floating point number, whereas everything else is an array of 4 floating point numbers. We have the texture transform, and it also has a required field. This time it's called text transform ID, and because text transform is 6 characters long, we're going to index from 7 onward. And the parameters we have here are scale, rotation, center, and translation. And rotation is a floating point number, whereas the other 3 are an array of 2 floating point numbers, as shown here. Okay. Next one is texture. Texture has a required ID of text ID, and it's an integer. And we have a file name, which is also required. So here we specify we want to return a char. followed after the text ID, which is also required. So both of these here are required. Now the reason why I know that they're required is just by looking at the return value. Anything that requires I specified as not equal to return, in which case it's going to return false. The ones that are optional, I use greater than or equal to return error no value. And I'll talk about this after we go into this find keyword so that you can understand when I return these specific values. It'll make more sense in a minute. So the optional parameters, we have the map, the quality factor, and whether it's solid or not. And all of these are integer values. Next we have the transform. And here we have actually we have no required fields for the transform, but we do have a bunch of optional fields. So we have the name, which is optional, and this is a char. We have the visibility is an integer. We have translation, center, scale, and axis. All of these, all of them are an array of 3 floats. So there we go. And the last one here is angle, and angle is just a regular floating point number. Now, one thing to remember is our structure. If we go inside, where can I show this? So I guess I can go into here. When we're loading in our file to be parsed, we might be loading in things like lights and shapes. Now, when we do parse them, though, we have to obey the structure that we've outlined inside of our game engine. And our structure says, for lights and shapes, you must nest them underneath the transform. So what that means is, if for whatever reason in here someone specified light, type, blah, 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 and so on, that would be invalid, because you can only have a light or a shape if there's a plus sign in front of it. If there's no plus sign in front of it, that means it's not nested, which means it's invalid. So the way we handle that inside the parser here is, in the root here, you'll notice that right now we are working directly inside of the parse line, so everything is in line here with this if statement. And if we find something called shape, then we automatically know the shape node must be nested underneath the transform, and we can return false, because we should not find anything called shape right here at this location. We're allowed to find shape or light underneath the plus sign, but that's handled down below. So if we find it here, that's an error. Same thing here with light. Light node must be nested underneath the transform and return false. So that's why we have these 2 cases here. Now we have the plus sign. The plus sign takes care of, where's my PDF here? Plus sign will take care of anything in here. So if we have a plus sign, multiple plus signs, as well as transforms, lights, and shapes, because those are the only things we should be able to find underneath here. So let's take a look at what we have here. First thing we do is we figure out how deep to nest this current node. So in other words, we need to count how many plus signs there are on the following line of text. So we start our counter here at number 1, because we know that we've already found one, because up here we branched into this if statement. So we know we have at least 1 plus sign. So then we go inside this while statement, and we go ahead and count how many pluses we find. If the number of counts that we're counting is equal to 32, we generate an error message saying that node nested beyond 32 deep. Remember, one of our requirements was you're only allowed to nest 32 deep, and that's the requirement for OpenGL, because certain video cards will not support pushing and popping the model view matrix beyond 32 deep. So that's why we need to specify here 32 deep is our limit. Now, what do we do when we're in here? Well, we're basically looking for the plus sign. If we find another one, we increment the counter and we go back to the while. So we continue doing that. As soon as we don't find a plus sign, we break out of this while loop. And then once we've broken out, we do some more checks. We see whether now we have a transform, whether we have a shape, or whether we have a light. And the location inside of our string that we start looking at is at the current index value of this count. So let's go back into PaintShop Pro here and see how this works. Imagine that we had a, let's say that instead of box here we had something called shape. And there were 2 pluses in front of it. Well, the way that our code is going to work is it's going to say, okay, go inside the first if statement because we found a plus sign here. So iCount is going to start off equaling to 1. Then we're going to loop through that while loop and we're going to find another plus sign. So we're going to say, okay, increment count, so count is now equal to 2. Then we're going to go look at this next index here and say, is this a plus sign? Well, no, it's not a plus sign. So it breaks out of the while loop. And then we say, okay, what is this string all the way to the end that we're looking at? And we're starting to look basically right here. So over here, we're looking at that string starting from the next location, and we're comparing it with transform or shape or light. If we find one of these, then we're going to go into the appropriate if statements. If we don't find one of these, then we automatically go into the else saying unrecognized nested keyword, and we return false because we don't identify what that keyword was that's nested. And what do we do under here? Well, as a matter of fact, we do basically the same thing we did out here for the specific nodes that is specified. So for transform node, we again check for all the fields that are optional because we have no required fields. So we check for name, we check for visibility, we check for translation, center, scale, axis, and angle. Now, only one thing you have to be really careful here is this value here. Before, you'll notice that for the transform node, which was up here, we use index 10. But now we need to take into account this offset of iCount because that offset takes into consideration how many plus signs there were in front of the keyword. So we have to add up this plus the size of the keyword to point to the next location in the string, which should be basically right here at where the first parameter is going to be specified. So we have to offset by the iCount. And then we look for the characters, integers, floating, and point numbers, and so on. So same thing as that we did before. For shape, we have the following. We have a required ID number for the GeoID. So again, we have iCount plus 6 this time. And then we also look for the name, which is optional, material ID, text ID, and texture transform ID. One thing which I didn't mention is all of these parameters here, you'll notice that I've typed them out in lowercase, and this is very important. Inside this document here, I wrote them out in mixed case, so the first character was capitalized and everything else was lowercase, but there's mixed case here. However, inside of the parser, make sure you type everything in lowercase because this function here is going to convert the whole string to be lowercase. So the only way you're going to be able to find it inside the string is if you compare with something that's already lowercase. So make sure that whatever you type in here is lowercase. All right. And then the last guy here, we have the light, and with the light source, again, it's a little bit more difficult because with the light source, we have a couple extra options. And actually, you're not going to see that here. You're going to actually see it when we implement it inside of our game engine. But the things that we're going to be looking for are the type, the name, whether it's on, what position is it at, the direction, the cutoff, the exponent, attenuation, ambient, diffuse, and specular. So those are all the parameters, and here are the types that we're looking for. Array 4, array 4, array 4 for all the color parameters, array 3 for the attenuation, floats for the cutoff and exponent, array 3s for position and direction, because that's a vector, and on is an integer, and characters for the type as well as for the name. And the only required one here is the type. Okay, so that pretty much wraps up the parseLine function. So we have our main function here, goes through every line of code, it calls parseLine. parseLine takes that one line of text and branches into the appropriate if statement for whichever section of code that we're looking for, whether it's a shape, whether it's a transform, whether it's a material, whatever. And each of these will automatically call this find keyword function, which will then do all the actual math and calculations to figure out what numbers are associated with these specific keywords that we want to extract data from. So let's go now take a look at this guy. Okay, so here we are, find keyword. At the very top, we create a couple variables for us to use. We have index A and index B, and these are going to be storing where inside of our string here, this guy here, do we find the specific keyword that we're looking for. We also create a constant variable here called notFound, which is equal to -1, and this guy stores the -1 value so that we can do a comparison anytime we do searches inside of the string. And you'll see how I use this in a second. So the first thing we do is we call setData find, and then we specify what keyword are we looking for. And this is going to return to us the index of where we find the specific keyword. If this index is equal to notFound, which is basically -1, then that means we don't find this keyword inside of our string, so we just generate an error message saying cannot find this specific keyword tag. And we return not found. If we do find it, this value here is not going to be not found. It's going to be some value that's going to tell us where inside of the string is this keyword. So let's go inside PaintShop Pro and take a look here. If we're, here, let me draw this. This guy here is the setData parameter that we pass into the function. And, oh, let me just move my table over a bit. So this guy here is the parameter setData. And its index here is now 0 rather than here, because remember we only passed in a partial of the full string into our function that does the searches. So this guy is 0, and we're specifying, okay, we want to look for a specific keyword. So our first keyword we're looking for is GOID_. And the function find is going to tell us where does this keyword sit inside of this setData. And it's going to return to us the beginning or the index number of where this guy starts. If we're looking for width, then it would return to us 0, 1, 2, 3, 4, 5, 6, 7, 8. It's going to return to us an index of 8 because that's where width underscore this keyword begins inside setData. Okay, so let's go back here and see. So index A contains the starting location of where we found our first keyword. We then look for a space following the keyword that we're looking up here. And the way we look for it is a little bit different. We specify, okay, we want to look for a space, but this time we specify an offset to start looking from. So, and the offset is going to be equal to whatever the value here was plus the length of the keyword. So in other words, inside PaintShop Pro, instead of starting at index 0, we're going to now start off at index 0 plus the width of this guy. So we're actually going to be starting looking for our string basically right in here. And whenever we find the space character, we're going to return the index value, and we're going to store it inside index B. If index B is equal to index A plus the length of this guy, then we generate an error message because there is no value after the underscore of the keyword that we're looking at. So we just say no number following this specific keyword, and then we return error no value. All right. If we get past those checks, we then know that we have the current location of where the number starts, or the character for that matter. It could be we're looking for a character. So then we have to branch into one of these case statements to determine what is the string we're looking for or what is the value that we want. So let's take a look at an easy one first. Let's take a look at float. The way we extract the floating point number from our string is as follows. We use another function from stdstring, and this one is called substring. So let's go inside MSDN here and take a look at substring. We need to pass into it a couple parameters. First parameter is an offset. The second parameter is a count. Both of these are actually optional. So if you don't specify them, the offset is going to be 0 and the count is going to be end position, which is all the way to the very end of the string. And if you read through here, you'll notice that what we're doing is we're extracting a substring of characters from a string beginning at the specific location. So in other words, starting at this location here, which is the starting location right after the underscore, we want to get the string that's located there. And because sz data is a string, we're going to return a string. But that's no good to us because we want to get a floating point number. So what we do is we take that string and we convert it to a char star. And we do that using the c_stdr. So this is going to now be a char star. With a char star, we can pass that into this function, atof, which converts a char star into a double. And then we cast that double into a float, which we then save inside this floating point number. So it's a little bit complicated. I could have actually rewritten this function or this work right here into 3 or 4 lines of code, but I just crammed it all into one because we want to, well, save on memory. I didn't want to create all these temporary variables that are just going to be wasted anyway. So I did everything all in one line, and I saved the value inside f value here. I then take and print that value to the screen using printf %s, so we specify the keyword, and then we specify the value that was just extracted, and then we break out. So that's how we handle floats. To handle integers, we do basically the same thing, but instead of atof, we use atoy, which converts a string into an integer. And this time we're saving the integer into I value, which we then print to the screen. So those are the 2 easy ones. The next more complicated one would be the character string that we want to return. Here, I create a temporary variable called sz_filename, and it's of size 256. What I do first is I clear everything in this memory space to be zeros. So I do that using memset. I specify I want this variable to have all zeros for up to the length of the string. So in other words, the entire size of the string. Then I use this function here, ss_scanf, to look inside of this string. Again, it's the same string we used before for all the floating points and integer numbers. And this time I say, okay, I want a string and I want to save it inside of this variable. And the string that I want, I limit to 255 characters because I know that my array here is only 256. So I don't want to overflow in case the string that's stored inside of this sz data is actually longer than that. So I specify I only want to extract the first 255 characters. And I save that inside of my variable. This guy will return a number, and the number it returns is how many string characters that it find. Since we're only looking for 1, it should return 1. If it's not equal to 1, then something went wrong, so I just return error no value. Otherwise, I just print whatever the keyword was, and then whatever the string value was that I found or extracted. So that's characters, that's integers, that's floats. Now let's take a look at arrays. An array of 2 floating point numbers is handled also using ss_scanf. And this time we pass in the string, and we're looking for floating point number, then we're looking for a comma, and then we're looking for another floating point number. And both of these numbers are going to be stored inside an array. You'll notice here I created an array of 2 floating point numbers. So the first parameter is the address of the first value inside of the array, and then the second parameter is the address of the second value inside of the array. So this function here, ss_scanf, is going to take the string, look for this floating point number, put it in here, look for the second floating point number, and put it into the second value. Once I have that, well, again, ss_scanf should return how many things that it converted. Well, I'm looking for 2 values this time, so it should return 2. If it's not 2, I generate an error message. Otherwise, I display the keyword I'm looking for plus the 2 values that I found. So float array 3 and float array 4, basically the same thing, but we're looking for 3 parameters. So here I have comma %f 3 times. And for 4 parameters, I do the same thing, array of 4, and we have 4 floating point numbers that we look through. Okay? So if you want more instruction on how these functions work, just go inside MSDN, type them in, read through the help. Oh, it's asking for disk here, maybe this one here. Let's see. Oh, this one's on my hard drive. So just read through the help here. If you don't have MSDN installed, you can also go onto the Microsoft website, and in there you'll have basically the same documentation with examples of how these functions work. Okay, so after doing all of the parsing here for the keyword we're looking for, the characters or the integers, the floating points, there's one other thing we have to do. And we have to check to make sure that the specific keyword we're looking for is the only instance of it on that line. So in other words, let's say someone had something like this, but for whatever reason, instead of having GeoID underscore 1 here, they had geo underscore 1 once, but then at the end they also had GeoID underscore 1. So they have this keyword inside the string twice. Well, that's invalid because we don't know which one the user intended to use. So what we can do is we can say, okay, look for this keyword, which again is the same keyword that we originally looked for, and this time we're starting to look from index location B. And remember, index location B was the location of the space character after the first time we found this keyword. So if we find this keyword after this space, which is located after the keyword, then we're going to save the index value here. If index B is equal to not found, then we return OK, meaning that, okay, everything's fine because we only found one instance of this keyword. If it's not equal to not found, that means we did find a second instance of this specific keyword. So we return error duplicate so that the user can then specify what do they want to do, because there are two duplicates of this one keyword on that one string of text. So there we go. That's the whole find keyword function. Now we can go revisit the parse line here and why this stuff here works. You'll remember I've always said that anytime we do a search for required fields, I do a not equal to return OK. Now this makes sense because if it's required, it has to return OK. If it returns anything else, so you'll remember these are the return values that it could specify. Actually, let me do this here. I'll just split my screen so we can see both parameters at the same time. Okay, so we could have return OK, return not found, error no value, and error duplicate. So if not equal to return OK, then that means this parameter, which is required, was not found. So we automatically return false. So that's the default for required fields. For optional fields, I do a check to see if it's greater than or equal to return error no value. Now, all enumerations, which is what this is here, are actually numbers. And you can see that here because return OK is equal to 0, which means the next guy is equal to 1, this guy is equal to 2, this guy is equal to 3. You can see that in the tooltip. Well, what I'm doing here is I'm saying if this value is greater than or equal to return error no value, which is this guy here. So if it's equal to or greater than 2, which means if it's this one or it's this one, then I return false because we generate no value or error duplicates whenever there's something really wrong. If we return not found, that is okay because this parameter was not specified, but that's okay because it's optional, remember? So it could return OK, it could return not found, and it's not going to go into here and return false. The only time it's going to return false if this function find keyword returns no error, or sorry, returns no value or returns error duplicate. So that's the way that the structure here works with these enumerations. So when you program this, make sure you order these in the same order that I specified, because I rely on the order of these guys for these checks here inside the if statements. If you reorder these, then you'll have to rethink the logic that you specify here inside the if statements. And as a matter of fact, when we port all this code over into our game engine, I think I did change the order of these because there was something that wasn't working properly. So we'll revisit that again when we go and port this code over. So there we go. Let's go and save this now and go build it and test it just to see if we can get it to run. Alright, so here we go. We see we're looking for a box, and here we found GeoID, so it specifies GeoID 1 has a width of 20, and it did not find a depth tag, and it did not find a height tag. It goes to the next guy, goes to the next guy, and so on, and then we close the file. So you can go in here and do a bunch of tests. Make sure that your parser is solid. You don't want to find bugs in your parser later on. So what I would actually recommend to you is go inside of this guy here and generate a LVL file that has every single combination possible so that you know for sure that your parser is working. Make sure you can extract data from every single parameter here under every single condition. And once you're confident that your parser is working, then go to the next video and start porting it over to the game engine. Because when we port it over, it's going to become more difficult to find errors inside your code. The other thing you can do when you're debugging is, here, let me demonstrate this. I'm just going to go replace this with some other code that I rewrote here, and let's go run through this. Alright, so here we can see, if we scroll to the top here, we have a box, so I've loaded in parameters and I can compare visually. Okay, GeoID 1, okay, that's good. Width here is 0.4, that's good, and so on. So you can go through, and you'll also notice that the order in which these appear here may not appear in the same order here, because the order that they appear on the screen is the order that they get parsed in, whereas the order that they're shown here is just any old random order. I can go and take these guys, reorder them however I like, it doesn't matter. The parser will still work and be able to find all the parameters. So make sure you do tests for that as well. And so you can just go through here. If you do find problems inside of your parser, what you can do is set up breakpoints. And the way you do that is very simple. For instance, let me just scroll down to parse line. Where is it? So at the beginning of parse line here, if you just click here, you'll create a breakpoint. Now when using breakpoints, you don't want to run your program using Control F5. Because remember, Control F5 is running your program without a debugger, whereas pressing this arrow here is running with the debugger. So if you want to debug something, set up a breakpoint and then press your start, or under debug here, press F5. Now when your program runs, as soon as it hits a breakpoint, your program will stop. And when it's stopped, you can actually go and take a look at the values that your code is looking at. So for instance, here, if I wanted to know, well, what is SZ data right now? Inside of the watch window, you can go in and type in your parameters, so SZ data, and you can see specifically, SZ data is equal to box space width underscore blah, 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 blah. So you can quickly debug your program to figure out whether your parser is working properly. So it basically stopped here at the first line of text because inside here, this is the first line of text that is called whenever parse line is executed. So now you can use the following keys on the keyboard. You can press F10 to go to the next line of code, F11 to go into a function. So you can use your keys on the keyboard, F10 and F11, to move through your program. You can also use, here there's these buttons here that step into, step over, step out of your function, show the next statement. So you can step into your code, so it's going into your code, step out of your code, and you can debug it very easily this way. I personally like using the F10 and F11 keys because you can step through your program very easily. You can also right-click and say run to cursor, so your program will run to wherever your cursor was just located. So now you can see here the current line of code is about to execute this line here, and if you look at SZ data, you'll also notice that everything here has been changed to lowercase, and that's because this function here got executed, so it already changed everything to lowercase. So you can, debug your code. If you need to set up more breakpoints, you can do that while the debugger is running. So I know you're going to come into here, so I can specify another breakpoint, say keep running, and then all of a sudden it stops at this location. So now, okay, it's at this location. What's it going to do next? Well, it just finished running this find function, and now index A is equal to 1. So here I can specify index A, index B, and so on. Index B is not defined yet, I have not set it to any value, so that's why it's this crazy big number. But if I continue stepping through my program, here this find function is going to return a value into index B. So as soon as I run it, you notice, oh, index B is now set to 8. So you can go through, debug your code very easily using these keys here, your watch window, and so on. And if you have any questions, feel free to ask me inside the forum on the website, specifically about something that may not be working for you. If you fully understand what the parser is doing, feel free to add your own functionality. Add extra keywords, add extra parameters, whatever you like. As soon as you have everything wrapped up inside your parser, it's much easier to create your game dynamically because you won't have to rebuild your program. I don't know if I demonstrated this before or not, but you'll notice now that, for instance, if I want to run my code, I can just run it. Oh, let me do this. Stop the code, debugging. If I run my code, it runs all the way through. If I go inside of the testing LVL file, I can make changes in here. Let's say I do this change here. I save the LVL file and I run my code again. My code did not have to rebuild because I didn't make any changes inside of the parser. All I did is I changed this LVL file. But because the code itself is loading LVL dynamically, anything that I change in here is not going to influence how many times I have to rebuild my program. And this is going to be huge whenever we port this over inside of our game engine, because we'll be able to create worlds dynamically using this LVL file without having to rebuild our code for our game engine. So that's a huge advantage for having a parser. Alright, so I think that's all I wanted to show you inside of this video. Again, if you have any questions, feel free to go to the website, ask questions, email me, whatever. And in the next video, we're going to start taking this code and porting it over into our game engine.